Thank you for the introduction, and thank you all for attending this presentation, even despite the slight shift in the schedule. Today, I'm going to present our project that is Network Testbeds as a Service for Application Development. We have here a brief outline of what will be presented. We'll begin with some introductions. Why Network Testbeds as a Service? Then we'll move on to the architectural details of what this project consists of. And if everything goes well, we'll have a live demonstration, and we'll finish with some results and the end time for questions. So first of all, who are we? We are researchers at Instituto Telecomunicações Aveiro. My name is João Capucho, and this project was made alongside two other colleagues, Igor Coelho and Zakhar Kruptsala, that due to some logistical problems couldn't be here in person. Why Network Testbeds as a Service? With the introduction of 4G, there was a growing, not need, but developers want to better integrate with mobile networks to provide value-added services to their customers. This began with 4G that introduced some APIs to access the telecom operators' networks, and was further propelled by 5G that introduced many more APIs. These are not only available to first-party developers, but also to third-party developers through the network exposure function in the 3GPP cores. The APIs exposed by the NEF are quite a bit complex, but very powerful. But for the majority of developers, this complexity doesn't pay off. So many initiatives, such as the Camara project, were created that abstract some of this complexity away. So at this point, we have broadly two API families, the NEF set of APIs defined by 3GPP and the simpler to use Camara APIs. But only having API definitions is not enough for developers. Developers also need some sort of reference implementation so that they can test their applications against and validate the behaviors. For the large majority of the development time, emulators can be used to supplant the use of a real network. There exists some such as the NEF emulator that in conjunction with some Camara transformation functions can also provide Camara APIs. However, when we reach the stage of validation and testing, this is not enough because some of the operations that are provided, such as network changing operations, such as quality on demand and traffic influence, can't be simulated with these emulators because they are simply using simulated devices that don't really exist. That's why network testbeds are important for application development, so that the developers can have these behaviors simulated in a realistic manner to validate their applications. There exists a potential alternative to network testbeds that is using a production network, but this is rarely possible due to mainly concerns about network disruption, and also it has a lot of associated costs, not only with the access, but also we need to have terminals, and there is also a large setup period with lots of bureaucracies in the middle. So we return to network testbeds, which mostly don't have these issues, but there is another big issue with testbeds for application development. They need to be isolated between different customers. We don't want them interfering with one another, not only because of technical reasons, such as consistent performance figures, but also due to some legal problems that may arise if the two clients have access to one another. Previously, setting up a network testbed required buying network equipment, setting it all up, configuring everything, and this not only was very expensive, but also introduced quite a lot of time between when a developer requests access to it and when they effectively could use it. This first problem of buying network equipments and setting it up were mostly resolved by the advent of virtualization. But the step of configuring everything is still present and is still quite a bit costly in terms of man hours. So the most logical step to take next is to also fully automatize the process of configuring the network testbeds. And if we then further build on top of this by making the whole process from ordering a testbed to the client having access fully automatic and driven by the developer, we can further cut the costs associated with this process and also the time between the developer requesting access and getting it. That is in essence what we mean when we talk about network testbeds as a service. Let's now talk a bit about the architecture. The most straightforward way to emulate how a network behaves is to effectively run a network using either an open source 5G core and a simulated RAN. However, this is quite expensive in terms of resources and computation and bandwidth, and it reduces quite a bit of overhead. And for the use case of application development in specific, this is not needed because many of the times the developers only want to verify that when they run the operation, for example, quality on demand, they see the new QoS profile being applied. So instead, we chose to actually extend an F emulator to contact an SDN controller to enforce these operations directly in the routing network. To do this, we required some SDN device that could function as a router, could be easily virtualized, and could perform some traffic policing and shaping to enforce the QoS profile. As it turns out, Linux can actually do this quite well. It has a traffic control subsystem that performs all of these operations. And so we can simply run a standard Linux VM acting as a router and have it enforce QoS profiles. Here we have a diagram of how it all fits together. Beginning with the client, it contacts the open source operation support system that in this case is OpenSlice. It requests, it makes a service order for a network testbed. Internally, OpenSlice will talk to open source Mano to deploy the testbed. This results in the creation of a network service that is composed of two VNFs. The first VNF is our Linux-based virtual routing setup that will be deployed through, in our case, OpenStack to our infrastructure. And then the other VNF is the one that will provide the NEF and Camara APIs that will be deployed as a KNF to a Kubernetes cluster. Then finally, we have the Linux router will integrate with TerraFlow SDN such that the NEF emulator can contact the TerraFlow SDN for it to change the QoS characteristics of the Linux router. As previously mentioned, there is a VNF comprising the Linux-based routing. This VNF is divided into parts. First, we have the client VM, that is the part that the client will have access to. This VM has no WAN access, and instead it does all its traffic through the other VM that is present, that is the Linux router. This is a VM that has access to the WAN and performs NAT from the client VM so that it can have access to the WAN. And all the traffic that passes through the client VM to the interface of the Linux router will have traffic control applied on it. So we can enforce there the QoS characteristics. In terms of the KNF responsible for deploying the NEF emulator and the MR APIs, that in this case are being provided by OpenOp, it's pretty standard. We are basically reusing the Helm charts provided by both projects. The only thing that of interest to mention is that the access to both of these APIs is made through a Kubernetes ingress that generates a domain automatically based on the service order. So now we reach the part of how do we effectively simulate the quality on-demand operations using Linux. As previously mentioned, this involves applying traffic policing and shaping to the interface that the client VM is connected to. Linux supports these kinds of operations through its traffic control subsystem that are defined as a set of queuing disciplines and filters. And in this case, when we are talking about applying QoS characteristics, we are mostly talking about actually applying impairments to the traffic of the clients. So we follow the QoS profiles to the letter. If they say the max upstream bandwidth will be this, then we apply it directly, which effectively means dropping most of the packets that are above that bandwidth. All of the traffic control subsystem on Linux is configured to the TC utility. So we reach the next problem that we faced when developing this project, that it is how do we invoke TC remotely to configure the QoS profile. This is where TerraFlow comes in. We are using it as an SDN controller so that TerraFlow provides its own API to its northbound interfaces for the clients to make changes to the network and provides a set of southbound interfaces. In this case, we are using the RESTconf southbound interface simply because it was the easiest to implement a device. And so we have our NEF emulator contacts the SDN controller to apply the QoS characteristics to our Linux router. TerraFlow then contacts our Linux router to RESTconf, and we have a small Python script that runs a simple web server that converts all of these operations to TC invocations. So this is basically the flow that I've previously mentioned. Initially, our wrapper contacts the TerraFlow to register a device. And then when the NEF emulator has a QoD subscription created, either directly or through the Camera APIs, it sends the NQoS profile for the wrapper that translates it into TC invocations. So now I'll be trying to do a little live demo. It begins in OpenSlice. We are going to have here the service for a network testbed. We follow the usual process of placing an order in OpenSlice, and then an admin will eventually look at the service order, and if everything is correct, it will acknowledge the order, triggering the full process of deploying this testbed. At this point, everything is automatic. The administrator doesn't need to do anything more. We are not going to wait for this testbed to deploy because it takes still a few minutes. And instead, we have already a testbed that I have previously ordered. Once the testbed finishes creating, we use the lifecycle rules in OpenSlice to actually populate these characteristics so that the user can know which domains it needs to contact to have access to the Open Exposure Gateway and to the NEF. We can see here these are running. These are the domains that were mentioned in that service. We have access to the Open Exposure Gateway. We have access to the NEF. And we also have here a command that we can use to access our VM. So if I now run this command, we have entered into this VM, and we can run our tests here directly, or we can use it to proxy. In this example, I'm going to run iPerf to test the network throughput. Right now, it's fully uncapped, so it runs at full speed. If I make a change to the QoS to our smallest profile, that should enforce a limit of 4 megabits, I think. And after it runs again, we have a small period where it's reconfiguring, so we drop some packets, and we can now see that our limit is being enforced. We also have another demo. Just a second. Yes, that's it. Where basically we are already using the smallest QoS profile, QoS, and we'll try to play back a video. This is video on demand with adaptive bit rate. So what will happen is right now we have a small buffer that was loaded before the QoS profile was applied. And once that buffer runs out, we'll have some buffering, and the quality should automatically drop to a smaller value. Not, or it doesn't work. Want to work now. Let me just reload the page. No, okay, no, it was my mistake. I forgot to proxy to our client VM. That's why it wasn't working. So now I've set up an SSH proxy. We have access to the video. I'm going to enforce again the smallest QoS profile. And once this buffer runs out, the video should automatically drop in quality. Should be right about now. I see exactly. We run out of the buffer, and the video to keep up playback, it reduced to 240p. If we now scale back up the QoS to our largest value, QoSL, once the video player notices, it will automatically increase. It will do so gradually until we restore the original quality. This concludes the demo. Let's switch back to the slides. So in terms of the results, we've managed to create a platform to deploy lightweight test beds in minutes. This can be done fully on demand by the clients, only requiring a little administrator input to ensure the service order is correct and approve it. And all of this is implemented using standard computing infrastructure, no special hardware needed. These test beds provide modern APIs to the clients that have real feedback when using quality on-demand operations. And all of this was done using only open source tools and projects, including some of ETSI's own software projects, namely OpenSlice, TerraFlow, OSM, and OpenOp. So what is next for this work? First, we are currently only simulating bandwidth in the QoS profile. We would like to add then latency, jitter, and packet error rates to complete the simulation. We had also originally planned to integrate CAPIF into the communication with OpenOp to provide security. But due to some time constraints, we couldn't do it. So we would like to revisit that. Then obviously we want to simulate more APIs that require this kind of network that have these network effects, such as connectivity insights and maybe also edge discovery. And finally, we also want to explore the idea of allowing through OSL ordering more client VMs to connect to the Linux router so that we can simulate multiple clients in the same network. Just to finish, all our code is available in the link present right now in the slides. We have an Helm chart that integrates OpenUp with NF emulator. We have the VNFDs and the NSDs that were used. And we also have the RESTconf wrapper that was mentioned. We also, in the course of this project, we encountered some issues and possible improvements in some of the projects used. We actually filed 2 issues and the corresponding PRs to OpenSlice related to some of the LCM operators, and also 2 issues and respective PRs due to some problems in the Helm packaging of OpenUp that I received an email just a few hours ago that were actually merged. So thank you for your work and in expediting that. And yes, that's the end of the presentation, and I believe we have time for some questions.